Welcome to DC 412, Understanding Wavelength of RF Currents in Feedlines. Before we start, I must say the allergy season has hit Texas. It's hit me hard. If I hesitate or my mic is muted for a while, it's simply because I don't want to cough in your ear. And if I wait for the allergy season to pass, I will never get this video done. When we talk about RF currents and feed lines, we're really talking about something completely different from an RF current in an antenna wire or an antenna element. This is because the effects on the antenna wire or element are rather minor, but in coax cable, there's so many things going on inside the coax cable that RF is propagated rather slowly through the cable. Fortunately, manufacturers can tell us exactly how fast their particular cable will propagate RF, so we can compute the length we need to do whatever it is we're trying to do. It all starts with that famous formula. You've seen this a few times before if you've watched my other videos. And yes, there's the rounded up 300 million meter number. There's the exact speed of light. But what do I use? Well, you can only cut coax cables just so accurately. I just stick with 300 over F in megahertz. It's close enough. You cannot cut the cable exactly enough to tell if you should use the exact speed of light or 300 million meters per second. So I just stick with 300 over F in megahertz. As I said before, coax cables propagate RF, I guess I would say kind of slowly. You're going to be surprised. In fact, it's so slow, we have to learn a new phrase, velocity factor. Velocity factor is the percentage of the speed of light at which the cable conducts RF. Most coaxes, as you see on the screen, have a velocity factor of 66 to 85%. And again, we don't use the term velocity factor when we talk about antennas or antenna wires. The factors that slow things down slightly in an antenna wire are completely different from what we're going to talk about here. And as I think I said already, the velocity factor rating of most coax today is tremendously accurate. If the manufacturer is a reputable manufacturer, they can tell you exactly what the velocity factor of their cable is. To determine the wavelength in coax cable is actually very easy. I use 300 over F in megahertz. I then multiply that result by the velocity factor. This gives me a length in meters. If I cut the cable exactly, I'm good to go. Now, as to the last bullet point, the only time you've got to be so careful that you consider the contribution the connector makes is at UHF, maybe VHF. In the HF range, the line is going to be so long that the slight variation the connector gives you isn't going to matter at all. But why would you care about the wavelength in coax? Well, generally speaking, we don't care. It does not matter. The amount of delay in a piece of coax cable means nothing to us. But once in a while, you'll run into something where this can actually be helpful. Say, for instance, my 2-meter repeater is producing a lot of second harmonic, and I don't know what to do about it. I'm near an airport, and interfering with 296 megahertz is not a good idea. I've determined that if I can get 20 or maybe 30 dB of attenuation, I'll be okay. So how do I do that? Well, here's my repeater. I've got my duplexer set up. I got the repeater itself. I got the feed line going to the antenna. What can I do here to null out that 296 megahertz signal? Well, there is a little trick you can use. The quarter wave coaxial stub is an impedance inverter. If I open the left end, just leave it open, the opposite end at the right shows a short at the frequency at which this is an electrical quarter wave. If I short the left end, the other end presents an open. So with that knowledge in mind, if I took an open-ended quarter wave stub and shoved it into an extra T connector, you see I've got a yellow arrow pointing at it, with the right-hand end of the coax open, the left-hand end will show a short if the cable is cut to a quarter wave at 296 megahertz. This will knock my little 296 megahertz interfering signal down considerably. Later, I'll show you how to measure how much it will knock it down. So all I have is a little math to do. I do the math, 300 over 296, a full wave is 1.01 meters. A quarter of that is 0.2525 meters, but my velocity factor is 0.66 on my coax. So that means RF propagates at 66% the speed of light, so I've got to shorten my cable to make up for that. So I come up with 168.3 millimeters. I have a metric tape measure, which makes cutting the cable to that length pretty easy. So that's what I do. I put a connector on, and you'll see the far end, which is on the left here, I'm holding in my hand on the right, and you'll see I've brushed all the copper wire away, insulated the center conductor from the shield. I have an open at that end. So first of all, let's see if I've cut it properly. Here's my test setup. On the top is a signal generator. Notice the green arrow. My output level is a minus 25.8 dBm. My output comes out of the coax cable with the number 1 arrow. That coax loops down to the number 2 arrow, and through a T connector goes into my spectrum analyzer. Look at the red arrow. It shows that my baseline at the top is about a minus 25 dBm. So that's my test setup. I'm ready to go. I add the quarter wave stub. Now look at the green arrow. I have not changed my generator output at all, but my red arrow has dropped. Each division on the scope is 10 dB. I'm down about 32 dB. I'll give you the math later on, but that's a tremendous improvement. So one more thing, you'll notice I actually cut my cable shorter than the math showed because the junction is actually at the yellow arrow or the yellow line under the blue arrow on the right. So from that yellow line to the other yellow line, I made that distance equal to my calculation of 163 millimeters. So you kind of have to take into account the length of the connector, and I also took into account the length of the T from the middle to the end of the connector. So I used my tape measure and measured from the yellow line under the one blue arrow to the yellow line at the other blue arrow. That's my quarter wavelength. But how does all this work? Why does a quarter wave stub do that? Well, let's take a quick look at Ohm's law. And we'll notice that if I put 100 volts on the line and have 100,000 ohms, I have almost no current. But if I put 100 volts on the line and have very low resistance, I have a ton of current. So high resistance is low current and low resistance is high current. That's pretty simple. Now, if I have a slight amount of current and 10,000 ohms, I'll have my 100 volts. But if I have a ton of current with almost no resistance, I have almost no voltage. So high resistance means high voltage, low resistance means low voltage. I'll come back to this, but I just wanted to show you the relationship between voltage, current, and resistance. I'll bring this back later. All right, let's consider this piece of coax. It comes in from the left. We don't care how long it is right now. But you see on the right, it's open. There's no connector, there's nothing. I'm going to shove some RF energy down it. But the RF energy has no alternative but to completely bounce back. All the power is going to radiate back. There's nothing that can change that. Now remember, in a previous episode, I said that the forward power was a traveling wave and the reflected power is a traveling wave. Well, the forward power is a traveling wave here, but the reflected power, actually in this case, is not a traveling, well, it's a traveling wave, but it doesn't change. What I mean is, at the end, we have an open circuit. So the voltage is going to be high and the current's going to be low, and nothing can change that. So in effect, my reflected power is a standing wave. It just sits there just like you see. Now, this is all very interesting. Where does this get us? Well, for a moment, let's do something interesting. Let's imagine this power being reflected back from the right. But let's cut the picture off one electrical quarter wave from the right. What do we have at that point? We have no voltage, but very high current. So at the very point we apply power, we are one quarter wave electrically from the end. And what we have is a very low resistance, so we have low voltage, and a very low resistance, so we have high current. This means we have a very low resistance. We have an electrical short at that point. This means that at the frequency that we're applying power, which is 296 megahertz, at the end of this quarter wave stub, we perceive a dead short. Now, interestingly, at the quarter wave point, we have a dead short. But look at the 3/4 wave point. The current's phase is reversed, but it's very high, and the voltage is still zero, or back to zero. What this means is a quarter wave stub and a 3/4 wave stub do the same thing. They present a dead short at the frequency at which they're resonant. So, I told you before that my stub was causing a 32 dB attenuation at the input to the spectrum analyzer. How much is that? Or how little is that? I guess that's what I should ask. Well, it isn't much. 32 dB means if I had a watt, I now have 0.00063 watts. Or if I had a volt, I have 0.0251 volt. Whatever that does mean is that I have attenuated my 296 megahertz energy going up the antenna line by 32 dB. If I was interfering with anyone before, I'm probably not even noticed by them right now. So you see, sometimes feed line length, or wavelength in feed lines, I should say, is actually very important. Feed line length is always important because it represents loss. But feed line length and wavelengths sometimes is a tool we can use, or it's an obstacle we might have to overcome. In the next episode, I'll talk about open wire and twin lead transmission lines, commonly called ladder lines. I'll also talk about things like the other neat things that a quarter wave or a three-quarter wave or a half wave stub can do for you. Because this is an extreme example of impedance inversion, but there are other neat things that these stubs can do for you. Anyway, thanks for watching. I hope this was worth your time, and stand by for the next installment, and I'll see you then.